This next reaction involves the reduction of carboxylic acids. Carboxylic acids are a bit difficult to reduce, so again we're using our most powerful reducing agent, lithium aluminum hydride. So in terms of just predicting the product, it's rather simple. All you really need to do is erase the carbonyl. So if I were to erase this carbonyl from the molecule, here I'm left with the alcohol product. Right now, mechanistically, it's not quite that simple as just erasing something. The other thing you might be kind of thinking about is the fact that we said lithium aluminum hydride and protons aren't compatible. And that's still true, but we can kind of take advantage of it in this reaction. So let's look at what's happening here. I'll fully draw out the OH bond, and here's the lithium aluminum hydride, and in this case I'm even going to draw out the full reagent and not just simplify it as H-. So what's going to happen in this first step is the hydride is going to come from the aluminum and take the proton. So this first step can be quite reactive, so you have to do it carefully and slowly. We end up with this carboxylate anion, plus you get hydrogen gas, plus AlH3. At this point, there's some different proposed mechanisms that you can draw to get to the final product. I'm going to show you one variation. So what can happen next is the AlH3 can add to the carbonyl. So let's draw that AlH3 out. So I'm going to do AlH2 and a single bond to one of the hydrides. And I'm going to add this across the CO pi bond. So now what we get, I've added the new hydride and the O bonded to AlH2. Then this oxygen with the attached aluminum can act as a leaving group. So I'm going to push this charge back down to form a double bond O and lose the oxygen leaving group. Now I have an aldehyde, and the rest of this is pretty straightforward. So you just add, you can just stick to a simple H- now. Add the hydride, and then finally step 2, when we protonate it, now we're left with the alcohol.